Hey everyone, here's our math problem for today. This is sent to us by one of our followers. Solve for the value of x, where x is an element of the set of real numbers, and we have this exponential equation. 49 raised to x minus 42 raised to x equals 36 raised to x. One strategy in solving this problem is to make the right side of the equation be equal to 1 by dividing by 36 raised to x. So let's do that. Divide this by 36 raised to x, and divide each of the terms by 36 raised to x. Divide this by 36 raised to x. Now, obviously the right side is now equal to 1. Then by the converse of the power of a quotient law of exponent, then we can write this 49 raised to x over 36 raised to x as 49 over 36 all now raised to x. So this is the converse of the power of a quotient law of exponent. We can do the same thing for the second term here. We can write this as a fraction 42 over 36 all raised to exponent x. Now notice that 49 is a perfect square, 36 is a perfect square. So let's write this as 7 squared divided by 6 squared all raised to x minus, notice that 42 over 36 can be reduced to lowest term as 7 over 6 all raised to x. The right side is equal to 1. Next, apply again the same power of a quotient rule of exponent. Then we can write this as 7 over 6 all raised to the second, then copy the exponent x, minus 7 over 6 raised to x is equal to 1. Then by a power of a power law of exponent, we can multiply the inner and the outer exponent. But since multiplication is commutative, we can also express this first term as 7 over 6 raised to x all raised to the second. We just interchange the exponent 2 and the exponent x, because when we multiply these two exponents using power of a power law of exponent, multiplication is commutative. We reverse the order of the two factors x and 2, and we just copy 7 over 6 raised to x is equal to 1. Now the beauty of this is, notice now that you have here the quantity 7 over 6 raised to x, and you have here the quantity 7 over 6 raised to x, which are the same, and therefore using substitution, we can use a different variable. So let's say, if we let a be equal to 7 over 6 raised to x, then this expression now can be written as a squared minus a equals 1, because the quantity 7 over 6 raised to x is a. We have here the same a raised to the second. Now let's write this in the standard quadratic equation so that we can apply the quadratic formula. So this is just the same as a squared minus a minus 1 equals 0. Now applying the quadratic formula, a is equal to negative b, so you have negative of negative 1, which is positive 1, plus or minus the square root of b squared, so negative 1 squared is positive 1, minus 4ac, minus 4 times 1 times negative 1, which is positive 4, divided by 2a, 2 times 1 is simply 2. So this gives us a value of a equals 1 plus or minus the square root of 5 over 2. Now, let's go back to our definition of a. We let a be equal to this value. And notice that the base is positive. When you raise a base to any exponent, positive or negative, you will always get a positive value. That means, since square root of 5 is greater than 1, we cannot take the 1 minus square root of 5. So in here, we just accept a equals 1 plus square root of 5 over 2. The 1 minus square root of 5 over 2 is an extraneous root. So we have here the value for a, and we have here our substitution for a. So a is 7 over 6 all raised to x, and the same a is equal to 1 plus square root of 5 over 2. Now let's solve this for x. So x is the exponent that is equal to the logarithm of 1 plus square root of 5 all over 2 to the base 7 over 6. Then from the change of base formula, we can write both of them as the logarithm to the base 10. So we write this as log to the base 10, we do not write that anymore, of 1 plus square root of 5 all over 2 divided by the logarithm to the base 10 of 7 over 6. Then using calculator, this will give us a value of x approximately equal to 3.1217. for the value of x. And so going back now to our question, the value of x in this equation is approximately equal to 3.1217. And we are done.